Okay, so we left off looking at how we deal with differences in sample means when we have sample variances. So today we're going to do one last type, which I mentioned a while ago. It was kind of going to be a new part compared to what we used to do with hypothesis tests, which is called matched pairs. So it's a little bit different of an idea, but it actually becomes a little bit easier than we were dealing with some of the other two population stuff. So let's get the slides pulled up here. So we'll work through some examples of this, and then we'll kind of transition to a little bit of Excel work today as well. So what we're doing with matched pairs is kind of like we have two populations, but instead of two completely different groups, it's like if we had the same individuals, but we're measuring some variable like in 2011 and then in 2012, right? A before and an after period, but it's the same individuals, right? So it's kind of like we have one population, but we're getting two kind of samples, right, of a before and an after time period. So you can do this with, not just before and after, and I think the Excel example I have we'll get at that, but usually it's going to be like a before and after. So we'll set up an example first to think about it. So let's say we've got a manager who's interested in whether or not productivity is increased or decreased after this workstation layout change. Kind of a goofy toy example. But what we're really thinking about doing here is, switch to the dot cam. We're waiting. All right. Can I zoom out a little bit? There we go. So what we're thinking about is, so maybe I have kind of all these different employees. That looks pretty choppy. Hold on, let me see if I can get we'll see if this shows up a little bit better. Okay. So maybe I've got, I don't know, John Smith, I don't know, Mary, I don't know, Jones, right? I've got a bunch of different people, okay? I'm then gonna have what their productivity was before, and I'm gonna have what their productivity was after, right? So maybe, I don't know, this is some units of something, right? So maybe this is 15, goes down to 11. I could have this for every single employee. So what I'm going to do is I'm going to create this difference variable, and I'm going to just basically create this new variable, which is the difference between the before and after. So kind of after minus before, like how much did productivity change? Well, for John, it went up by 2. Mary, it went down by 4. I would then do this for every employee. Right? Once I've done this for every employee, I've essentially now just have one variable, which is this difference variable, and I can start to do things like calculate the average difference, right? And get the variance on that difference variable. Well, once I have the average difference, that's essentially like I have a one population sample mean example, right? So I'm going to have this sample difference and the variance of that difference. So what it's going to become is, now I'm thinking about what's the distribution of that sample difference. Well, it should be, if I have a sample size over 30, should be centered around whatever the true difference is. When I do things like hypothesis testing, I'm now going to have an assumed true difference. I'll have the variance of these, I'll have the variance of that difference variable. So I'll know that if I want to think about the variance of my sample differences, that's just going to be the original variance of that difference variable divided by my sample size. Well, this is really the exact same setup we had with a one population sample mean example, right? Before where I have a sample mean, I now have a sample difference. Before I had an assumed true mean, I have an assumed true difference. And then if we're thinking about the variance in our sample means, well, that was just the variance of the original variable we sampled from over our sample size. So everything's really the same. It's just we're kind of indicating now that we're not looking at kind of a quote unquote normal, just single variable. We're looking at this variable that we created, which is the difference between two other variables. Okay? But once we get to this point, confidence intervals, hypothesis testing, everything's going to look just like it did when we had a sample mean, right, and only a sample variance. It's going back to the stuff we did before the exam. Oh, so if we only have a sample variance, right? We only have a variance of this difference variable. We're also going to know that we're going to be looking at student t distributions, but our degrees of freedom, because it's like we have the same individuals, we really only have one population, goes back to simply being n-1. So it makes things actually a little bit easier than it did when we had two different populations and we had the difference in sample means, okay? So it's a little bit different, you know, like before what we were doing was we had two different populations. So it was like we would calculate a sample mean and a sample mean and then look for the difference between the two. That would be like if we only had before and after productivity measures, but we had like 20 different employees in each population. Now we've got the same 20 employees, so we can calculate this difference variable and kind of stick with one population, okay? So if we think about doing this match pairs, I've got my sample difference and I've got the variance on that difference variable. Well, my confidence interval simply becomes, I'll build the confidence interval around the sample difference that I found. I have to use the student t distribution, find a t-value that gives me alpha over 2 on either side of my confidence interval. The degrees of freedom goes back to n-1, and then I multiply that by the standard deviation of the differences in my, the standard deviation for the sample difference, right? Which I know will be equal to this. So just to kind of line that up with what we've done in the past as well. Before, what we were doing with one population and sample mean examples looked like this. Where this represented the standard deviation of my sample means. Well, now I'm just going to build my confidence interval around that sample difference that I found. And now it's just the variance of that difference variable over my sample size. This kind of representing the standard deviation of my sample differences. So same sort of setup. It's really just we're adding, you know, everywhere we had an x before, now we've got this d representing that difference variable. Okay. So it's going to look like nothing really new. So if we work through an example, let's say this manager goes through, has, you know, I forget, I think I only said 10 employees here, which should have a higher sample size, but just for the sake of having a number in here, it should be okay. As long as the original difference variable we sampled from was normally distributed, the central limit theorem would be met, so we'll just assume that for now. So we have this sample difference of 8.5, the variance on that difference variable of 121. If I want to build a 95% confidence interval, what do I need to do? Well, if I think about the equation, I've got my sample difference of 8.5. I've got the variance of 121. If we go back, I think it was 10 employees. All I have to do is find that t-value. So if I had 10 employees, actually maybe I should double check and say that to see it was 10. Yeah, 10 workers, okay? So if I have 10 workers, my degrees of freedom, right, is n-1, so 10 minus 1 is 9, right? So I've got my degrees of freedom of 9. The 95% confidence interval, alpha would be 0.05, but there's half of alpha on each of my tails, so 0.05 over 2, 0.025. So that's where that 0.025 is the area I want in the tail. I have degrees of freedom of 9. Let's go to that t-table. I'm going to have to scroll way up here. So I wanted 0.025 in the tail. My degrees of freedom is 9, so I'll see where these two meet. 2.62. Now I've got that t-value I need. I've got everything plugged into my equation. Now it's just a matter of, oops, I can get back to the right slide. There you go. Now it's just a matter of plugging all those values in. Okay. So this isn't really anything new here. The only new part was that we had to calculate this difference variable ahead of time, right? And then we just simply find the average, find the variance, and it becomes a one population example where we only know kind of a sample variance. Okay. Any questions on that before we keep moving? Okay. So I've got this range of values, you know, if we can kind of interpret this, 0.6 to 16.37. So the only values are positive. So with 95% confidence here, I could say that the change in productivity was positive, that it increased, right? Which seems like a pretty applicable thing that I might want to be able to say, if I had an actual product and I actually, could think about the quantity of their production, what it actually, maybe it was, the number of, I don't know, automobiles or engines or whatever we want to think about there. Or maybe, the number of documents that they're putting out. So pretty relevant example. But if we can do confidence intervals, we can do hypothesis testing as well. And it all goes back to, it's the same thing as what we were doing with one population examples where we had a sample mean, but only a sample variance. So, instead of the means now, we're going to be looking at the mean of that difference variable and have an assumed true difference, right? But kind of already mapped this out for you, right? So we know that the distribution of our sample differences will be built around that assumed true difference. We can do a right, a left, or a two-tailed test, just like we did before. And our test statistic looks almost the same as what we were doing before. It's just everywhere we had an X, now there's a D, right? Because we're not just looking at a regular X variable, we're looking at this difference variable that we created. So our test statistic, if we want to match this up with what we were doing before, so we had everything going on with our confidence intervals. But before, our test statistic was take the sample mean, subtract the assumed true mean, divide by the variance over the sample size, where this denominator represented the standard deviation of my sample means. Now my test statistical equation, I take my sample difference, subtract my assumed true difference, and then divide by the square root of the variance on that difference variable over my sample size, which this represents the standard deviation, standard deviation of my sample differences. So this should be D kind of bar, S subscript D bar. Here, I'm going to write this out because that looks terrible. There we go. Okay. Well, now that we have the test statistic equation, everything's going to look exactly the same. So let's say we have that same example, and I want to calculate my test statistic. Well, it's just a matter of plugging my values in, right? Now that I know this is the equation for my test statistic of a sample difference, it's really just a matter of plugging this in. And once again, I'll keep this assumed true difference at 0, right? So that almost makes this a little bit easier than what we were doing, even with the sample mean examples that we did prior to the last exam, okay? So we've got this test statistic. We want to do the critical value approach. Oh, sorry, I didn't even fill this one out. So I calculated the test statistic here. Let's say I want to do the critical value approach. I'll add some stuff in here that's not on the slides. Well, my degrees of freedom is 9, right? Let's say I didn't really give you a test here, like one or left, right, or two-tailed test. But let's assume we want to do a two-tailed test. Okay? So we're going to do a two-tailed test using that assumed true difference of 0, and we want to find the critical values. Well, if we have a two-tailed test, we automatically should know that what we're doing, well, we only have a sample variance, so we're now using that student t-distribution. And we're trying to find critical values such that there is a total of alpha in these tails, which means there would be alpha over 2 in each tail. Okay? So if I think about, if I wanted to find critical values for every alpha, so 0.1, 0.05, 0.01, then the areas I want in each tail would be alpha over 2 would be 0.05, 0.025, and 0.005. So these are the 3 areas I want in the tail at a degrees of freedom of, remember we had 10 workers, so n minus 1 would be 9. Okay. So I go to my standard normal table. I want 0.05, just a reminder, 0.05, 0.025, and 0.005 in the tail at degrees of freedom of 9. So 1.833, 2.262, and then 3.25. Those would be my critical values, right? But I would have kind of pairs, right? So however we want to do this, plus minus, I already forgot what they were, 1.833, plus minus 2.262, and then plus minus 3.250. So those are my 3 critical values. I could then plot these, right? So the next step, if I can get the paper There we go. So what I'm thinking about now is I've got this student T distribution. Someone left their water bottle here and it's getting in my way. Think about, I got something like this. So I'm going to plot all these critical values real quick. So we got what? 1.83, 2.26, 3.25. These are all negative. 1.83, 2.26, 3.25. I can even draw the arrows, kind of give me a nice visual of where my rejection region is. And now the only thing left I have to do is plot my test statistic. Okay. And I already forgot what that was, so I'm going to go back. It was 2.44, right? So 2.44, if I plot that test statistic of 2.44, I can see that it's in the rejection region at these two levels. Just as a reminder, this corresponded to 10%. My marker almost rolled off on me. 5% and 1% levels. So I can reject at the 10 and 5, but I would fail to reject at that 1% level. Okay? So we work it out just the same way we would for any other two-tailed test, going back to those one population. Well, really, once you have the test statistic, all of hypothesis testing should look the same. Any questions before I move off this screen here? I'll leave it up for a second longer. Okay, so we can do another example. Where are we at on time? Oh, we're good. Let me think if I want to go through this first. Yeah, I'll go through these first, and then we'll go do some Excel. So let's say you've got a nutritionist, and they have before and after calories consumed for Starbucks card holders. Before and after, they kind of started posting what the calories were of their items. So you've got 40 different individuals. You have measures of how many calories they consumed before Starbucks posted the calories in the menus, and then you have how much those same 40 people consumed after they started posting. So you find that a sample difference actually of 2.1. So you actually find this positive kind of change. Right? You also see that the sample variance on that difference variable you collected was 64. You wanted to calculate a 99% confidence interval for what that true difference is. What would it be? Okay, well, we've got our sample difference. We think about this confidence interval. We've got our sample difference of 2.1. We have the variance on that difference variable of 64. We've got 40 card holders. We just need to find that t-value, right? So our alpha, the 99% level, will be 0.01. So there's going to be half of alpha on each side. So 0.01 divided by 2 is 0.005. Our degrees of freedom, well, if our sample size is 40, remember degrees of freedom is just n minus 1. Excuse me, so 40 minus 1, our degrees of freedom is 39. So 0.005 at a degrees of freedom of 39. Go to our t-tables, 0.005, degrees of freedom, scrolling all the way down to 39, 2.708. Well, now that we have that 2.708, now we have everything we need to plug in and calculate that confidence interval, right? And at that point, it's just a matter of getting entered into our calculator correctly, right? But we have all those values plugged in, and we get this lower and upper bound of negative 1.3 and 5.53. So if we're trying to interpret this confidence interval, at the 99% level, what can I say about the average change in calories consumed? Well, I can't say much, because remember what we're doing here. When I have these values, whoops, got way more sheets on here than I thought. So we just said, I think it was negative 1.3, and I forget the exact value, it was 5 point something. Let's say it's 5.2. The true difference, right, population difference, is somewhere in this range. So the true kind of average difference could be negative, could be positive, it could even be 0. Could even be that there was no change, right? These are just all the values that could be the true population difference. Okay? So we can't really say much with this confidence interval, right? If they were all positive values, we could say that the true population difference was positive, that calories is consumed have went up. If it was only negative values, we could say that the true difference is negative and that calories consumption has went down on average. Right? But based off what we found, we can't say anything because it includes positive, negative values. It also includes 0. Okay. And then I always liked this meme. So if you haven't seen this movie, Napoleon Dynamite is like an old cult classic. Came out when I was in high school. It's incredibly stupid, but will still make me laugh. So I always suggest go check it out. It won't waste too much of your time even if you don't like it. So let's say we keep running with the same example and we want to do the we want to test for whether or not calories consumed at Starbucks have decreased after kind of posting the calories on the menu. So we want to see for whether or not it's decreased, so that difference is negative. So what we want to test for, that alternative hypothesis will be, is that difference below 0, right? Is it negative? We then assume the opposite is true, which is that it's greater than or equal to 0. Okay. So I think identifying these for the matched pairs, it's a little bit easier than with the other two population stuff. But once we have this alternative hypothesis, we know we have a left-tailed test, right? Less than sign in the alternative hypothesis, we have a left-tailed test. And the assumed true difference value we should be using is 0. So if I look at the evidence that I found, I find the sample difference and the sample variance, and I want to calculate my test statistic, well, automatically, right, if I find a sample difference of 2.1, because I'm always setting these examples up for you, where the assumed true kind of average difference is equal to 0, but when I see a sample difference of 2.1, remember, when we're calculating test statistics, all we're really doing is converting that sample difference we found into either a z or a t-value, in this case, a t-value. So what is my test statistic here? Well, if I found something that's above the assumed true value, right, above the assumed true mean for this statistic, well, then I'm going to be a certain number of standard deviations above, so my test statistic should be positive. Right? If I'm thinking about if I was to turn my assumed true difference here into a t-value, it should always be 0, right? It should be centered around kind of whatever that assumed true difference is. So I know my test statistic is positive, so right away I can rule out A and C, right? If I plug everything in here, I've got my sample variance, my sample size, the average difference, the assumed true difference of 0, I get about 1.66. Okay? Now, I'm showing you this to give you an example of calculating a test statistic. But if I have a left-tailed test, what sign would my critical values be? Well, if I'm thinking about a left-tailed test, I automatically know that when I look at that t-distribution, my critical values for a left-tailed test should be negative, right? They're on the left side of that distribution. That distribution is centered around 0. I know the area to the left and right of 0 is 0.5, and I'm looking up alphas like 0.1 and 0.05. So the area to the left of my critical values is much less than 0.5. So I know that it's going to be a negative value. Well, I found a positive test statistic, right, 1.66. So automatically, I know that I'm not going to be anywhere near my rejection regions, right, because my critical values should be negative. So this is one in which if you're just trying to make the rejection decision, automatically we know, yeah, I don't know what the critical values are, I haven't looked them up, but I know that I'm going to reject, right? Because I know that they should be negative and my test statistic is positive. Okay. Any questions on that before we keep moving here? Okay, so that kind of takes us into this example that I have using suicide data to kind of test for whether or not there's differences, right? So let's go back to that two population hypothesis testing blank file we've been working off of. I actually believe, I kind of remember doing this. Hopefully I did. I didn't want to say, yeah. So I have the one that's up to date with all the work we've done in class. So if you want to kind of pick up from this one, you can, but the original file that we've been working on is this blank one. So we did some stuff on the male data sheet and the South data sheet. So let's look at this suicide data. So I have this difference variable calculated, but I'm just going to kind of get rid of this to show you. So let's say it came in like this. Right? I don't have, maybe I don't even have the stuff set up here. So I want to do something about, you know, instead of doing time periods, right, I'm going to actually look at the same counties, right? So I've got different time periods, but I've got the same counties, right? And in that county, I'm going to look for the difference between kind of male and female suicides, right? So I've got rates, but I'm also have male and female suicides here. Okay? I could do the rate variable. It's probably a little more appropriate, but in terms of when we get to the interpretation, it's just a little bit easier to think about the number of suicides here because, you know, the number of deaths is a little easier than kind of the number of deaths per person, or, you know. So we'll just use the suicide variables here for ease. All right, the population's the same. It's the same county, and I just have male suicides in that county and female suicides in that county. Okay? So instead of having a before and after period, I've got kind of male and females. Right? So I can look for the average difference in male and female suicides. So I think I had this set up as male minus female. So all I'm going to do is go over here and take the male suicides in that county, subtract the female suicides in that county. Nice, easy way to then create the rest of this difference variable. So you could like hold this and go drag it all the way down. Or once you get this like big bolded plus sign, if you double left click, it should take it all the way down to the very bottom of the data sheet. Right? So you now have this difference variable calculated. So if I want to find the average or the mean difference of that difference variable, I can use that average function in Excel. Control Shift or Command Shift on a Mac and hit the down arrow. We'll select the entire variable. We can use that var.s, sample variance. We've used this, you know, plenty of times at this point. All right. Select that entire variable. So Control Shift or Command Shift, hit the down arrow to do that. And then of course our sample size, we can use that count function. Control Shift, Command Shift on the Mac, hit the down arrow, hit enter. We've now got our sample difference, or our mean. You can almost think about this as our mean difference variable. I don't know why I unbolded this. So, all right, here's our mean difference variable. Here's the variance on that difference variable. Here's our sample size. And if it helps, right, this is only a sample variance because we're calculating this from a sample of counties and years. Right? I'm going to put that hypothesized true, or kind of the value from our hypothesis test in this cell here, just for when we calculate our test statistic later, we'll use that. But now from here, it's just a matter of building our kind of either confidence intervals, or we can do some hypothesis testing. So I'll build the confidence intervals for you first. Right? So what are we doing here? All we're going to do, try to make this a little smaller here. Oh, where was this? We had it earlier. I had the equation written down. Okay. We're basically just going to use Excel to be a calculator. We're going to put this formula, when we subtract the lower bound, add our upper bound. We'll just use Excel to be a calculator. But we'll also use Excel to look up this student T value. Okay. So here we're going to find our lower bound and our upper bound. Well, the first thing that we need is, well, what are these T values going to be that we have? So, just like we did for the difference in sample mean examples, we're using the student T distribution, and we want to find the T value that gives us alpha over 2 on each side. So we're working in reverse because we know the area in the tail, so T dot INV, right, or inverse. Okay. We then tell it the area we want is alpha divided by 2, comma, what's our degrees of freedom? Well, that would just be our sample size minus 1. Now, this is always going to look at the area in the left tail. So when we hit enter, we'll get the T value that we want, but it's negative, right? So kind of the trick that we've said we've been using, because the positive and negative sign are already built into the lower and upper bound equation. We'll just take the absolute value of this. Now, when I copy this down, I want my alpha values to change, but I need that reference for the sample size to stay exactly what it is. So I'll put dollar signs around that. So this should give me my lower bound, or sorry, this should give me the T value that I need to calculate that lower bound. Great, I'll copy this down. I've got the T value I need for each level. At this point, it's just a matter of using Excel to be our calculator and get this entered in. So move this down here so we can see this. So we'll take our sample kind of mean difference, right? Subtract that z value multiplied by the square root of our sample variance of that difference variable divided by our sample size. Now, when I copy this down to get the lower bound for the next 3 levels, I want everything to stay the same except for the t-value, right? I'm basing it off the same sample difference. I'm just going out a little bit wider when I want to get a higher confidence level. So highlight this, hit F4 or Command T on a Mac, we'll freeze these. The only thing we don't want to freeze is that t-value. So now when we copy this down, we get our 3 lower bounds. How do we get the upper bound? We said just go into that very first lower bound. We will copy that formula, hit enter to get out of the cell. We'll paste it to get our upper bound. The only thing we need to change is that negative sign needs to become a positive sign. Once we have that, we can copy that down, and now we've got our 3 kind of confidence intervals. Okay? Notice the higher level of confidence, the lower bound's getting lower, the higher bound's getting, or upper bound's getting higher, so we've got a kind of wider confidence interval there. Okay. Any questions on that? You want to see a cell again, or get this to show the chat? There we go. Okay. So the next thing we need to do is find our test statistic. Right? Once again, it's really just using Excel to be our calculator. We have our test statistic equation here. So all I'm going to do is enter that in. So equals the mean difference minus the assumed true difference divided by the square root of my sample variance over my sample size. It's that easy, right? We're just using Excel to be our calculator. We don't even have to type numbers in. We're just literally clicking on numbers. So this should give us our test statistic of about 39.6. Okay. Now, I don't believe I have it kind of set up here. So if you want kind of a reminder of this, so let's do a right-tailed test. What we want to look at is that assumed true difference. And here I'm going to not waste time like creating substrate. So is that, I guess here on our null hypothesis, we'll create our alternative hypothesis, which is that true difference greater than 0? So we have a right-tailed test. We'll do the exact opposite for the null, which is that it's less than or equal to 0. Right? So I'm just not going to waste time creating really nice equations here, but just so we have something to kind of reference. Well, first of all, I found a ridiculous test statistic. I mean, hopefully we've had enough practice at this point where we realize like this test statistic is going to be so much larger than any critical value we look up, and that the p-value is going to be so incredibly small, the area to the right of that test statistic, that I should definitely be rejecting here. But I just want to walk through and make sure we know how we can find critical values, find p-values. So for our critical values, right, we've got our test statistic. We could think of our critical values are going to be corresponding to different alpha values, right? So our alpha values that we're going to look at are 0.1, 0.05, and 0.01, kind of our 3 benchmark values. Just like when we had the difference in 2 sample means, right, where we only had sample variances, our critical values, we know the area in the tail, we want to find the t-value that gives that to us, so we use that t.inv function. Okay? So equals t.inv. The area we want on either side of our confidence interval is alpha divided by 2, comma, our degrees of freedom will be our sample size minus 1. And now, kind of one thing we have to make sure we do here is realize, oh, we're doing a right-tailed test. So if I'm looking up the area to the left, right, I want alpha over 2 in my upper right tail. So I can do kind of 1 minus alpha over 2 would be the area to the left. If I want kind of a visual, what I'm thinking about here, draw a new one here. So let's say, right, if I'm just looking up one critical value, I want the critical value that gives me, you know, alpha over 2 in the upper right tail. So the area to the left would be 1 minus alpha over 2. So that's what I'm telling Excel. If I want to copy this down, I want the alphas to update so I can find 3 critical values very quickly, but that sample size reference, I want to stay the same. So I'll freeze that. Now when I copy this down, I get my 3 critical values. Notice it should be the same as what I was using for my confidence intervals here. Actually, why did no one corrected me. It's not alpha over 2. I'm not doing a two-tailed test. Sorry, this is just alpha. Right? They should be different. I'm not doing a two-tailed test. I'm doing a right-tailed test. So I shouldn't be dividing alpha by 2 here, right? Because there should just be alpha total just in that one tail. Sorry about that. I wasn't thinking about what I was doing. Okay, so we've got alpha total in the tail, so 1 minus alpha would be the area to the left. Now I've got my 3 critical values. Okay. So I could plot my test statistic against those. I mean, if we look, that 39 is going to be so far to the right. I mean, we're going to be rejecting at every single level here. Okay. Now, if I wanted to kind of build in those rejection decisions, I'm going to use the p-value approach because I think it's a little bit easier. So we're going to put the rejection decisions in here at the different alphas. And I could do that, you know, comparing the absolute value of my test statistic, the absolute value of the critical value. If the test statistic's larger, I reject. But I always, you know, kind of like to do the p-value approach. So what was our p-value? Remember, our test statistic is like 39, right? So here's our test statistic. The p-value is the probability we see that or anything more extreme, or in this case, for a right-tailed test, the area to the right. Okay. So I know my test, I know my t-value. I want to find the area to the right of it, so I can use that t.dist. Now you'll notice there's kind of a helpful additional function that we didn't really have for the normal distribution, which is .rt. Right? So I tell it my test statistic, comma, my degrees of freedom, which was the sample size -1, and it'll give me my p-value. Now it's incredibly small. We shouldn't be super surprised about that. What I could have also done is just use the regular t.dist, tell it my test statistic, comma, my sample size -1 is my degrees of freedom, comma 1, so it's always giving me the area to the left. I know I wanted the area to the right, so I could just subtract that from 1. Now, they're formatted a little bit differently here. Let me see if why isn't this showing up? So sample size -1, t.dist, comma 1 minus. I mean, these are basically the same. I think I could play around with getting the format to be the same so they match up. Let me see. Format cells. We'll go scientific. Hit OK. Well, there must be a little bit of a rounding that's a little bit different in that .dist, but it's basically right. We get the p-value of basically 0. And I'll show you these line up a little bit more when this isn't so close to 0 that there could be rounding errors. Right? Now, what we could also do, right, is use that built-in t.test. Right? So t.test was that kind of shortcut we use where it calculated the test statistic behind the scenes, then it spit back out as the p-value. So the 2 arrays that we will select if we use the t.test method, we didn't have to create this difference variable ahead of time. We just select the original variable. So we'll go over, I'll select male suicides, so starting with the very first data point. I'll go up to this little formula where I can put a comma. So I selected that first variable, which was male suicides. Second variable is female suicides, so I'll select that, comma, I'll scroll all the way back up so I can show you what we're doing. So those are the first 2 things, right? The first 2 arrays, right? My 2 data points. The next is the number of tails. Well, I've got a one-tailed test because I've got a right-tailed test, comma. The type of problem I'm doing is a matched pairs example. So before, when we were looking at the difference in sample means, we put a 3 in there because we had 2 samples with unequal variances. Now, we put a 1 because we've got a matched pairs example. Okay? If I hit enter, this is basically going to do a very similar thing. Notice, once again, there's some rounding differences between these built-in functions, but we're getting pretty much 0 here. Okay? So it's basically what it does, that t.test, it's going to take the male and female suicides. It's going to, behind the scenes, create this difference variable, calculate the mean difference, sample on that difference, sample size, calculate your test statistic, look it up in the right student t distribution, and then kind of spit back out at you your p-value, okay? So any of these methods will kind of give us our p-value. Any questions on anything? Oh, I forgot, I didn't finish this out. First of all, any questions before I can do? I've got a couple more things and we'll kind of wrap it up. Okay. So, you know, I could use that if statement thing if I wanted to do, you know, if my p-value is less than alpha, comma, put in the word reject, comma, if it's false, we'll just put in the word fail, right? We fail to reject. Now, when I copy this down, I want the alphas to change, but not my p-value. So I'll put $signs around that. Now, when I pull this down, now I've got my rejection. Now, we had a crazy low p-value, so we should always be kind of rejecting here. But really what we were saying was, is the difference between male and female suicides, is it greater than 0? Well, we found pretty strong evidence that on average, per county, the average difference we found was 44 more male deaths than female deaths, right? And a pretty high sample size. So maybe we could start to think about, well, not only can I just say, is it greater than 0, is the difference between male and female suicides greater than 20, right? So I go up here, I change that 0 hypothesized true value to a 20, right? What is this doing? Yeah, the t dot this must just round it a lot differently. Now notice, if I change this here, I can get my p-value to change, and I could even test, you know, is it greater than 40? I still can definitely reject that it's, you know, if I think about testing for is it greater than 40, I'm assuming it's less than or equal to, so I can say with 99% confidence that the true difference between male and female suicides in a county is greater than 40, right? Or sorry, it isn't a value that's less than or equal to 40, right? So I know that the true difference is something above 40. So we can start to play around. I don't know exactly, oh, we can't do that. We can do 43. And then I start to maybe fail to reject differences like 43. But, you know, even at a difference of 40, I can still reject with 99% confidence. Notice once we start to get p-values that look a little more realistic, those rounding errors, you know, that are out to whatever decimal aren't causing any difference in our p-value calculation here. But the problem is, just like with a t-dot test, when we look at difference in sample means, that t-dot test, there's nowhere where I can put in a hypothesized true value, so it always is using that value of 0, right? Notice, no matter what this is, the t-dot test doesn't change. It can only do a hypothesis test for that value of 0. Okay. All right, any questions? So if I go back to 40, I can kind of see that's why there's a difference there. Any questions over that? I'll change it back to 0 before I post it, re-up or replace the old one so that has all this new additional work today as well. Okay, so that kind of wraps it up for hypothesis. Well, we'll do a little bit more of hypothesis testing, but not as near in detail of the process. We'll just kind of reference it. What we're going to do, excuse me, for the rest of this week and next week is something called kind of linear regression. We'll kind of really just do the basics. It's a lot more interpretation than it is computation, but we will be doing some things in Excel with it. So be prepared to kind of have it, you know, have Excel open, or at least, you know, be taking really detailed notes about how you do things in Excel. Because I will probably even after Wednesday's class post that last Excel assignment. I've already kind of mentioned I dropped the lowest, so in a way it's optional if you've done the first 4. It shouldn't be too intensive in terms of the computation. Like I said, it's going to be a lot more interpretation. I think you'll kind of see what I mean once we actually start working through some examples and I introduce the topic. It's the last topic that we'll cover before the final exam, okay? I've also, and you can look at it, but a lot of this stuff, you know, will be some of the linear regression things we haven't covered. But I put a final exam, so we go to files. There's already a folder up there, final exam practice materials. It'll have a formula sheet and kind of the practice exam. So it's only going to be on things since the last exam. So haven't had a lot of time. Here, I'm going to switch it back to me to end this. So we haven't had a lot of, you know, time post that second exam. You know, we're having this week and next week, so another couple weeks. But it's really going to be the extent of the content is more limited, right? So we basically just have two population stuff, so differences in sample means, sample proportions. Sample means are when we have sample variances, the match pair stuff we did today, and then linear regression, right? So a little bit more limited in scope. So you want to take a look at kind of those practice exams to give you some material that will help you the closer we get to that exam, studying for that. Okay. It should cover unless there's any questions. Okay. All right. I will see you guys on Wednesday.